the 8th lesson of this series of video, Mathematics of Quantum Mechanics, and today we would be discussing the most fundamental and perhaps the most important fundamental concept of quantum mechanics, that is vector space. Now, vector space are very central to quantum physics, and the entire mathematics happening and the concept of quantum mechanics revolves around this single concept, vector space. So in today's video, I would be going a little bit deep into vector space, giving you certain very simple examples how the vector spaces gets expanded from the general Euclidean space, the bra and the cat notation, and a little bit more about Hilbert space and various other fundamental concepts. So my request to you would be not to skip any part of this video, because vector space is the central idea of quantum physics. My name is Shaunak and I welcome you to watch this video on my channel Physics for Students. A warm welcome, and also a special note of thanks to everybody who has been putting up comments, especially to support this series of Mathematics of Quantum Mechanics. Okay, so first let us quickly see what are the topics we are discussing today. We would be first understand a general vector space. Then we will see how the vector space is getting generalized from the Euclidean space to further complex places. We will understand what are the properties of vector space, what is the cat notation, what is the inner product, and how vector spaces get generalized to n dimensions. Most importantly, we deal with the complex vector space in quantum mechanics and why at all we need quantum mechanics needs these complex vector spaces, how and why we cannot do it in normal vector spaces. We will also look into examples of complex vector space, the bra and the cat notation, and a little bit about Hilbert space, because everything in quantum mechanics happens in Hilbert space. So said and done, these are the topics. So first we will understand what is a vector space. Now let me tell you that vector space is a concept mathematicians have developed. I mean to say many mathematical concepts that later was found important in physics. Now, one of the important of these concepts is what we are dealing today, that is vector space, and it describes a certain physical space, right? So in addition to this, there are more abstract concepts which are used in vectors in physics. The concept of complex vector spaces, however, falls in the heart of quantum mechanics. So it is very important for us to understand. So the collection of complex vectors of a given dimension with vector addition and scalar multiplication is called a vector space. So in mathematics and physics, a vector space is also called a linear space, and it is a generalization of Euclidean vectors which allows modeling of physical quantities into vector space. Physical quantities like force and velocity, they have not only magnitude but also direction. And when we go into vector space, these are characterized by their dimensions, which roughly speaking specifies the number of independent directions in the space. Now, this is not true. Dimensions are not always number of independent directions, but just for the analogy of understanding, it roughly speaks of the number of independent directions in the space. This means actually that for two vector spaces with the same dimension, the properties that depend only on the vector space structure are exactly isomorphic, or you can tell that these are absolutely the same. Okay, so this is given a fair understanding of what is a vector space. In the Euclidean space, generally we denote the scalars as often real numbers, so and it goes into field, the force and velocity, and it gets generalized to vector space. So if we set all the n-dimensional vectors, we call it as an n-dimensional vector space. Okay, so there are certain properties. So if we take the collection of mathematical objects in a scalar multiplication, then there are two important properties. First is that the set is closed. Now we will come to what we know as set is closed, but let us understand the set is closed under addition and scalar multiplication. That means the resulting of adding of two arbitrary objects from the set, it also is in the set. The second is that the set of addition and scalar multiplication will follow the following properties. Now these properties I'm just quickly skipping over because these have already been discussed in my previous videos in Mathematics of Quantum Mechanics. It follows the properties of commutativity, it follows the property of associativity, and it also follows the distributive law of scalar multiplication. If you want to take a pause right now and just check on these vectors and how it is you can. However, these have been discussed at length in my previous videos. Right. So we turn the page and we come to this, the distributivity of scalar addition, which is this one, and there exists an additive 0 denoted as 0 such that v plus 0 equals to v, and for any vector there exists an additive inverse, that is v plus minus of v would be equal to 0. Okay. Okay, so just now I would like to give you a kind of a visual depiction of what is a vector space. So let us understand that a vector space is a collection of elements, right? It is a kind of an element. It can be anything. It can be a tiffin box. It can be a bus. It can be anything. So I just want to make you understand that vector space is a collection of elements. These elements can be thought as momentum and velocity. These elements can also be thought of as arrows pointing in certain directions. Now again, as we go more into abstract mathematics, it would be unwise or it would be wrong for us to imagine always a vector by a straight arrow. No, vectors are not always straight arrows, because vectors in complex mathematics and complex planes become something else. Okay, we will look into it. Now we will use the notation of this one to indicate a vector with a label A, and this is called the ket notation. Okay, don't worry about bra and ket. These will require a separate video, and I am just in the process of making a separate video on the notation, how the Dirac, these are called Dirac notation, right? It has been invented by Paul Adrian Maurice Dirac. So how the bra and the ket, operator behaves, or what are the ways in the coefficients are put up. It's pretty simple. It's just a representation of quantum mathematics. So I will make it. So for the sake of understanding, let us understand this is called a ket. Now, as I told you, it has been invented by Dirac and has been used. Now, there are two defined operations which the vector space is closed. So I was telling that the vector space is closed. So one is that addition of vectors, which can be this, the ket multiplied by this, and another can be multiplied with a vector by a number. So I just consider this to be alpha. So closed actually means that the operation yields a vector in the space, that is a plus b equals to c, and alpha multiplied by a will yield to some other number. So just to tell you that this is another definition of what is a vector space. Okay, so as I was telling that vectors can also mean arrows in physical space, which are length in direction, and we can further use the law of parallelogram in order to do all those vector additions. Again, if you go, I am actually making two parallel videos series, I would say. One is linear algebra, that is a separate playlist that contains in details all those things. Not only parallelogram or the triangle equality tools, but I have actually gone further and proved these laws. So if you're really interested just to know linear algebra, go to my series in linear algebra playlist, and one by one it is there. But however, this series only concentrate on that level of mathematics which is just required to understand and get the quantum physics better. So this is parallelogram law. The second is that scalar multiplication doesn't change the orientation, so it is its length. You see this blue one, it just shows, I'm so sorry, this actually shows the multiplication, that means it doesn't change the direction. The scalar, the scalar multiplication by a negative vector actually inverses direction. So you can see this blue one, so it just changes its direction. This, I mean to say, just simple. Okay. Now here is something which is called an important concept, which is called inner product. Okay. Now inner product, dot product, these again will require a separate video to understand. If you really want to understand very detailed about dot product and inner product, go to my playlist in linear algebra, and you will see there is a dot product and an inner product. That is a separate video given. Even I have made you understand about the practical usage, how computer graphics, computer games, solar panels uses dot product and inner product. This is one video which you can check it in my linear algebra playlist. The second is called dot product, inner product, outer product, and I think, yeah, there are 4 products which is there. So dot, inner, outer. So right for this moment, let us understand that inner product is basically for, we are interested in vector spaces which has an inner product, And inner products is nothing but this is an operation on two vectors which yields to number. So here is a space, right? A real vector space and a complex vector space. So in this case, the inner product is a familiar dot product of two products. So I've just taken the component of ax and bx, and it can be easily shown that it leads to ab cos theta, which is something very simple like this. So here a and b denotes the length of the arrows, and a and theta is actually the angle between them. What is important is that the inner product actually shows that the dot, or you can say the inner product, is independent of the choice of vectors, basis of vectors. So whatever the vectors you're choosing or you're selecting, it is independent. So just to tell you that, let us understand that because we are understanding vector space, vector spaces, we are interested in those which have got a kind of an inner product. So this diagram and the blue dot actually shows the real vector space and the complex vector space and how the inner product operates. Okay, I will just give you a few quick examples of what are the other examples of vector space. It's not always that these are the examples. Quickly, I will show you. So besides the 2D and the three-dimensional arrows, we can also see about a one-dimensional arrow. So these are the numbers on the real line, something like this. So the real line numbers form, actually you can tell, one-dimensional vector space. So far, now the thing is that so far we have only considered physical arrows. Now let us consider and step more into the abstract vector spaces where the space is not a physical space. And here comes the most difficult, and most of the students get confused, and here is my job to clear up the confusion, is that vector space is not a physical space now, because in quantum mechanics we do not deal with physical space, a space where you will keep your pen, paper, shirt, pants and tie. No, it is not a physical space. So for example, a collection of this 2 by 2 matrices, this can also be a vector space, right? You can easily show that it satisfies the closure that we have seen under matrix addition and matrix multiplication by the real number, right? So that is one. Another is that although we can think about 1, 2 or 3 dimensional space, we can fairly easily abstract the idea of a vector space in higher dimensions. Just a note that let us not try to vision or envision by closing our eyes into 4, 5 or 6 dimensional arrow. We cannot really do that because our brains are hardwired to only able to think on 3 or fewer dimensions. So even though we cannot envision vectors of more than 3 dimensions, we can easily abstract the idea from the mathematics. And here it is, a vector space of n dimension has got n basis vectors, and these would lead to n vector components. And this is the infinite dimensional vector space, and this space has infinite number of basis vectors. And further you can see this one A1, A2, and this can be a vector space in n dimension. So you see the mathematical abstractions are not really difficult. Only thing is that we always try to close our eyes and try to imagine the vector spaces and other abstract ideas in terms of the physical objects that we see around, a cup, plate, tea, chair, etc. But mathematics really doesn't work like that. Okay, so let us go to the next level of abstraction. Now in here what happens is that till now we have been considering something which is continuous. So then the components, rather being a function of the discrete index I, will be a function of a continuous variable x, and it will look something like this. So the set of real analytic function on a given interval form an infinite dimensional vector space. Yeah, so if you get an infinite number of components, one for each value, the continuous variable x are needed to specify a vector or a real function. It is easy to show, most importantly, that the set of all analytic real function on a given interval satisfy the closure conditions. Sorry. And by what do I mean by all analytic functions? That those can be written in the form of power series. So that means it is infinitely differentiable, and we can say it something as well behaved. So here is we are taking discrete basis vectors. So the inner product of two vectors A and B can be written as something like this. Very simple. So sorry, I'm using the sigma because it is all discrete. Now, for the case of the vector space of real function, the sum over products of the components now becomes an integral. So if we take two functions f and g, remember that this is the ket notation we are using, and we get something like this. Okay, so this is something which again is a further example of vector space when we are not considering the basis vectors to be discrete but something which is continuous. We come to the next important part, quantum mechanics and complex vector space. Now, before going deep into this, what I would like to tell you is that there are a few postulates, just like special theory of relativity, general theory of relativity. Quantum mechanics also have a postulate. I will find out a separate video explaining each of these postulates. I think I have done, yes, there is one video in my series in quantum mechanics where you can see. Now, one of the postulates of quantum mechanics actually says this. Okay, the state of system are described by vectors in the complex vector space. So the first question which we are addressing is that quantum mechanics deals with complex vector space. Why? Because one of the postulates, which is the Copenhagen interpretation of quantum mechanics, tells that the systems of a system, the states of a system are described by complex vector space. Now you might ask me why, right? Now you need to go back to my another video which is there in my first and second video of this series, Mathematics of Quantum Mechanics. I've explained why complex number is required in quantum mechanics, and I've also explained why complex planes or complex vector spaces come. But anyway, you really don't need to go there. I will just explain you in simple language. We all know that in quantum mechanics actually deals with the wave function which is given by the Greek letter psi. So what actually this psi denotes is the possible outcomes of measurements such as an electron's possible position or momentum. It is not certain. So all it does, it creates a weird kind of a probabilistic world where there is a possibility whether it can be here or there, etc. Now, if I take the general kind of a space here, you will see that I have just written the Schrodinger's equation in a short form. So here also the equation itself comes across complex numbers, right? Now, I have taken a general wave which moves along the this x-axis, and what I have seen, what I have got here, I'm just taking a snippet of my earlier video, so pardon me, I'm not explaining this much because again it will take some time. So here you will see the exponential goes up to negative I omega t and then a positive I omega t. So what I am trying to tell is that the positive and the negative frequency is a general movement of a wave have to be present in equal measure. That means there has to be a positive and a negative. So if I take the Greek letter psi and it is somewhat equals to the exponential of minus I omega t, so what happens is that it allows for wave-like phenomena and at the same time allow only positive frequencies, and complex function must enter into quantum mechanics. So if you see the earlier video, I explained in detail that when we allow only positive frequencies, the complex functions, and thereby the complex vector space comes into it. Okay, let me show it in a fresh kind of a page. Yeah. So what happens from here is that as you see that these things go into complex numbers, so obviously the complex numbers won't play their role in the normal real number vector space. So quantum mechanics uses the complex vector space as it allows to do operation which is not possible in classical mechanics. Also, the complex numbers themselves from a one-dimensional vector space, right? And a complex vector space is one in which scalars are quantum numbers, complex numbers. Okay, so before I go into this, I think that this is a time just to give you a reminder that the earlier video and here I have shown that the quantum, the normal wave equation, and if you use them in order to get a positive and a negative, it requires something as a complex number. If it comes as a complex number, obviously, as you see in the left-hand side figure, I have given the one part is the imaginary, another part is the real, and because quantum mechanics all deals with imaginary, so complex vector spaces will come. So I will just again define a vector space a little bit on a definitive way. So the real vector spaces are real, and in complex vector space is one in which the scalars is complex. So I will take these numbers v1, v2, v3, dot, dot, dot up to vm. And these are vectors in a complex vector space, right? Let me write it. Yeah, vectors in a complex vector space. And then we can form a linear combination where I C means complex, right? I should have written it. Anyway, C1, V1, C2, V2, dot, 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 where the scalars C1, C2 are complex numbers, and it goes up to n dimension. It goes up to the linear combination. So the complex version of Rn, I mean to say real number up to n dimension, is the complex vector space, I can say, of Cn, or we can consider Cn, whatever. So a vector in this Cn has this form, right? A1 plus B1I plus A2 plus n, it goes up to this. Okay, so I will just show you a pretty simple example, because without example things are not clear. I take a kind of this one, a vector in the Cn form, and I take another vector as U. These are vectors in C2 form, that is in 2 dimension, and when I add this I get this. That's simple, nothing more, just showing you that how the vectors really operate. Okay, so let us consider 2-dimensional complex vector space, again an example, and we choose here 2 basis vectors, right? I'm selecting, what I'm doing is that I'm selecting 2 basis vectors, 1 and 2. I'm just selecting it just for the sake of giving you an example. Now what happens is that if I take a general vector as A, then a linear combination of the basis vector yields to this, right? A11 plus A22. Okay, so this is now a complex number, and now let us not try to think of complex arrows, because things will further get complex. So that is why I told you that it is not always that vectors are arrows, so sometimes it becomes very weird. So let us not think it. Now, for a complex vector space, we need the concept of the complex conjugate of a vector. If you really don't know what is a complex conjugate, go back to my first 2, 3, 4 lessons in this series in quantum mechanics mathematics, and you will understand. So what we do is that we denote the complex conjugate of this ket with what is called a bra vector. And if I know that if A, this one, I mean to say, is equals to A1, A2, then we give it like this. So the row and the column interchanges. Don't worry about this. The stars are basically the complex conjugate. So I will be explaining further on bra and ket notation. This is just to give you an idea. So if we take forward with this one, what we can say from here is that definitely there is a one-to-one correspondence between the ket vectors and the corresponding dual bra vectors. Now you might be asking me, what is a dual bra vector? Hold on for this video. This is something I need to expand further, which is called a dual space. I will do it in that. So from still now it is quite clear that how the bra and the ket vectors actually have a one-to-one correspondence and how they change. Now what we can do is that we can define the inner product of a complex vector, something like this. It looks weird, but don't worry. And the reason for defining the inner product is that the inner product of a vector with a vector itself, so A with A and so on, is itself real and positive. Here you see here, this one is basically the length and the norm, and this one, the entire thing, is the inner product of a vector with itself is real and positive. So for a complex vector space, I mean to say, when we are defining the inner product, it looks like this. And the reason for defining is that the length of the inner product with the vector itself is considered real and positive. Just note that the reason for writing the bra as a row matrix and the inner product is because it will follow the matrix multiplication, as we have seen here. And don't worry, we will do a lot about matrix multiplication in the upcoming videos. Right. So finally, what I would like to give you a complete overall picture is that let us imagine this to be a space. Now, whether you imagine as a physical space or not, it is up to you. But this is just a space where we get certain values. For example, psi1, psi3, and psi2. So these are what? I mean to say, you already know these are quantum state. So I can call this blue one as a Hilbert space. And how can I define easily a Hilbert space? I can define that Hilbert space is a space, or you can consider it a table or a pillow cover or something which is populated by all possible states that a quantum system can be found. What do we mean by quantum system? Just on a very rough way, it is a mathematical entity that provides a probability distribution but the outcomes of each possible measurement of the system. So you just remember that I told you that electrons behave in a weird manner, and we just can find out the probability distribution of where can the electron be. So here it is. So here is a space which is a Hilbert space. It is populated with different types of numbers which we will explore slowly, and these are all possible states where it will be this, that, etc. that a quantum state can be. And the quantum state is basically provides a probability distribution for the outcome which is responsibility on the measurement of the system. Now when I talk of measurement of the system, again there are various other reasons, experiments, foundings, we will come to that later. Now this Hilbert space actually is equipped with certain properties. One is superposition, one is dimensionality, one is normalization, one is basis, and another is completeness. We will see further in the next videos coming up that Hilbert spaces, some of the, I would say properties matches with the regular vectors. I mean, regular, vector spaces. So superposition, dimensionality, normalization, basis, and completeness is something, what are the properties of Hilbert space, and we will cover up the Hilbert space and its properties with certain very simple examples in the next part of the video. So in the next video, we would be covering the properties of Hilbert space. I will take a little bit more time to explain more into complex vector spaces, and then we will start with the matrices and matrices operation, because that is again central to understanding the mathematics of quantum mechanics. Thank you very much for watching this video. Please put up your comment, how do you find, any suggestion, etc. And please subscribe to my channel, Physics for Students. Click on the bell icon and click on all to get all the notification from physics students. Coming up next very soon, we will continue this series on quantum mathematics of quantum mechanics, and stay tuned for more interesting videos on physics and mathematics. This is Shaunak signing off right from today, promising you to be back very soon. Till then, goodbye and have a nice weekend ahead.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment, or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram, and LinkedIn. See you soon in the next video.